2. Graphical description of longitudinal waves. Similar to transverse waves, we also use displacement distance graph and displacement time graph to describe longitudinal waves. A. Displacement distance graph. For the snapshot of wave, also called a waveform, we may deduce a displacement distance graph, which shows the displacement of particles at different positions at a certain time. In this case, you may first identify a few particles with zero displacement, such as C, G, and K. They are either centers of compression or rarefaction. Note that, just like the motion of simple pendulum, the particles with zero displacement are traveling at the greatest speed. Remember, they are not at rest. When we take the right direction as positive, we can easily measure the displacements of different particles to draw the following graph. Now you may identify the particles A, E, I, and M are all at their extreme positions. They are all mid particles between a compression and a rarefaction. In other words, the particle just midway between a compression and a rarefaction has the greatest displacement, and it is momentarily at rest. Now, if you focus on the center of a compression, you can see it has zero displacement, which means this particular particle does not move at its own original position, while the particles on the two sides move towards that center of compression. Similarly, the particles at the center of a rarefaction also has zero displacement. Only the particles on the two sides move away from that center and then create such a rarefaction. Lastly, if the wave travels towards right, you may sketch the displacement distance graph a very short time later. And now, you can tell that particles B, C, D are moving towards right. F, G, H are moving towards left. J, K, L are moving towards right. And lastly, A, E, I, and M are all momentarily at rest. Example 3. SD graph. The wave is traveling to the right, so we take the right direction as positive. Carefully examine the displacements of the 7 particles. There is a pattern, and you can easily deduce the displacement of the 8th or 9th particles. And in this case, you can tell the wavelength. On the other hand, you can also find half lambda first, as from the graph below, which is the separation between the equilibrium positions of F and J. Lastly, you have to find a particle vibrating in antiphase with K. Try it yourself. By the way, do you know the particles G, I, H are all moving towards right now? Scale. It was found that the center of compressions and rarefactions both have zero displacement. The particles on the left of a compression travels to the right, while particles on the right travels to the left. If the right direction is taken as positive, then the y-x graph at the center of compression has a negative slope. On the other hand, the slope of the y-x graph at the center of rarefaction has a positive slope. Do check point 2. On the next page,